Using factoring to solve polynomial equations. A quadratic equation in one variable is an equation that can be put into the form ax squared plus bx plus c equals 0. Zero factor property. Let a and b be real numbers. If a times b equals 0, then a equals 0 or b equals 0. In words, if the product of two numbers is 0, then at least one of the numbers must be 0. In this example, we need to solve t squared plus 4t minus 12 equals 0. So we begin by factoring. We need two numbers that multiply to be negative 12 but add to be 4. So we have t plus 6 times t minus 2 equals 0. The equals 0 is important because we're doing an equation. 6 times negative 2 is negative 12. 6 plus negative 2 is a positive 4. Now we want to use the zero factor property, so t plus 6 equals 0, or t minus 2 equals 0. Adding the opposite, t equals negative 6, or t equals 2. We can check our work by substituting to the original equation. Let's start with t equals negative 6. So we have negative 6 squared plus 4 times negative 6 minus 12 equals 0. Negative 6 squared is 36. 4 times negative 6 is negative 24 minus 12 equals 0. 36 minus 36 equals 0, so 0 equals 0. I can do the same check with t equals 2. 2 squared plus 4 times 2 minus 12 equals 0. 4 plus 8 minus 12 equals 0. 12 minus 12 equals 0. 0 equals 0. So both of our solutions are correct. In this example, solve x squared equals 11x plus 12. In order for the zero factor property to work, it has to be equal to 0. So our first step is to bring down our x squared, subtract 11x from each side, subtract 12 from each side so that it equals 0. We need to factor. We need two numbers that multiply to be negative 12 but add to be negative 11. So x minus 12 and x plus 1, and bring down your equals 0. Negative 12 times 1 is a negative 12, and negative 12 plus 1 is a negative 11. Now setting each of them equal to 0, x minus 12 equals 0, or x plus 1 equals 0. Solving for x will be 12, or x will be negative 1. I can check. First, I'm going to substitute in for x equals 12. 12 squared equals 11 times 12 plus 12. 12 squared is 144. 11 times 12. 11 times 12 is 132. Plus 12 gives us 144 equals 144. So we know that x equals 12 works as a solution. Now check x equals negative 1. So I have negative 1 squared equals 11 times negative 1 plus 12. Negative 1 squared is 1. Negative 1 times 11 is negative 11. And negative 11 plus 12 is 1. 1 equals 1. That one checks as well. Connection between x-intercepts and solutions. Let f be a function. If k is a real number solution of the equation f of x equals 0, then the ordered pair k, 0 is an x-intercept of the graph of the function. Also, if the ordered pair k, 0 is an x-intercept of the graph of f, then k is a solution of f of x equals 0. This property suggests that we can verify our solutions of a quadratic equation ax squared plus bx plus c equals 0 by using a graphing calculator to find the x-intercepts of the graph f of x equals ax squared plus bx plus c. In this example, solve 2x squared plus 13x plus 15 equals 0. 2 times 15 is 30. 13 is my b. I divide by 2. I need two factors of 30 that add to be 13. So 3 and 10. 10 over 2 reduces to 5 over 1. So I can factor this into 2x plus 3 and x plus 5 and bring down the equal 0. Using the zero factor property, I set each of them equal to 0. So 2x plus 3 equals 0, or x plus 5 equals 0. Going back to the 2x plus 3 equals 0, subtract 3 from both sides. 2x equals negative 3. Divide both sides by 2, x equals negative 3 over 2. For x plus 5 equals 0, subtract 5, and x equals negative 5. So my two solutions are x equals negative 3 over 2 and x equals negative 5. So going to my calculator to check my work, we want to go to y equals, and there we want to type in our function 2x squared plus 13x plus 15. I'm going to go to Zoom and choose the standard plot 6. Now that I have my graph, one of the options I have is I can use trace. I start with my y-intercept, which is 0, y equals 15. I can use my left arrow to move the trace. So here I get negative 1.5. It's very close to 0. That's negative 3 over 2, one of our solutions. I keep going to the left. The vertex. Then I continue to go to the left. And x equals negative 5 when y equals 0, which was our other solution. So our two solutions are correct for this problem. I can also go second, graph, which gets me to my table. And if I arrow up, I'm looking for my y1 to be 0. So I have x is negative 5 when y1 is 0. And because of the way the table is set up, I can't see my other x-intercept. Second window allows me to set my table. I'm going to leave the table start at negative 7 because that was in the area we needed. I'm going to set the TBL from 1 to 0.5. Then second table, I arrow down. Now I can see both my solutions. Negative 5, 0 and negative 1.50. So that's the second way that we can verify our answers. One is by using trace, and the other is by going to our table. For this example, we want to solve x squared minus 10x plus 25 equals 0. I need two numbers that multiply to be 25 but add to be negative 10. So x minus 5, and bring down the equal 0. Using the zero factor property, I set each of them equal to 0. So I have x minus 5 equals 0 or x minus 5 equals 0. Solving each of them for x, I end up with the same answer, x equals 5. Verifying this on my calculator, go to y equals, clear out what's there, I type in x squared minus 10x plus 25. Go to graph. And notice that the vertex of our parabola is on my x-axis. Anytime our equation has only one answer, the vertex is going to be on the x-axis. If I push trace and then arrow, this time I'm going to arrow to the right. And I get that x equals 5 when y equals 0. So our answer is correct. Graph of quadratic equations. The solution set of a quadratic equation in one variable may contain two real numbers, so the parabola will cross the x-axis twice, one real number, so the parabola will cross the x-axis once, or no real numbers. The parabola will not cross the x-axis at all. In this example, solve x squared minus 5x equals 35 minus 3x. Our first step is to get this equal to 0. Bring down my x squared. If I add 3x to both sides, negative 5x plus 3x is negative 2x. Subtract 35 from each side, minus 35 equals 0. I'll need two numbers that multiply to be negative 35 and add to be a negative 2. X minus 7 and x plus 5, and then bring down the equal 0. Using my zero factor property, x minus 7 equals 0, or x plus 5 equals 0. For x minus 7 equals 0, I add 7 to both sides, and x equals 7. X plus 5 equals 0, subtract 5 from both sides, and x equals negative 5. To check this, y equals, I type in x squared minus 2x minus 35, graph. Second table, so negative 5 is one of my answers, as is 7. Since we had to set the equation equal to 0, you should also check this in your original equation. So checking, I'm going to start with x equals 7, so 7 squared minus 5 times 7 should equal 35 minus 3 times 7. So I have 49 minus 35 equals 35 minus 21. 49 minus 35 is 14, and 35 minus 21 is also 14. So x minus 7 is correct. Now checking x equals negative 5, I have negative 5 squared minus 5 times negative 5 should equal 35 minus 3 times negative 5. So that gives us 25 plus 25 equals 35 plus 15. 25 plus 25 is 50, and 35 plus 15 is also 50. So x minus 5 also works. For this example, solve parentheses x minus 4 times parentheses x minus 3 equals 2. For this one, we still need to set it equal to 0, but we also have to deal with our parentheses. That gives me x squared minus 3x minus 4x plus 12 equals 2. Bring down my x squared. Negative 3x minus 4x is negative 7x. I need to set this equal to 0, so if I subtract 2 from both sides, 12 take away 2 is 10. I have x squared minus 7x plus 10. I need two factors of 10 that add to be negative 7. So x minus 5 and x minus 2, and make sure you have your equal 0. Setting each of them equal to 0, x minus 5 equals 0, so x equals 5. Or x minus 2 equals 0, so x equals 2. Now I can do my check, starting with x equals 5. 5 minus 4 times 5 minus 3 should equal 2. 5 minus 4 is 1 times 5 minus 3 is 2 equals 2. 2 equals 2. Now using my 2 minus 4 times 2 minus 3 should equal 2. 2 minus 4 is negative 2 times 2 minus 3, which is negative 1. Bring down my equals 2. Negative 2 times negative 1 is 2. 2 equals 2. Both my solutions are correct. In this example, we want to solve 3/8 x squared minus 1/4 equals 5/8 x. Since I have an equality, I have the option of eliminating my fraction. The least common multiple for 8, 4, and 8 would be 8. If I multiply the whole equation by 8 over 1, I would have 8 over 1 times 3/8 x squared minus 8 over 1 times 1/4 equals 8 over 1 times 5/8 x. 8 over 1 times 3/8, my 8's cancel, and that leaves me with 3x squared minus 8 over 1 times 1/4, I can cancel out my 4, so my result is 2 equals 8 over 1 times 5/8, my 8's cancel, leaving me with 5x. So 3x squared minus 2 equals 5x is a much simpler equation to solve. Subtracting 5x from both sides, I end up with 3x squared minus 5x minus 2 equal to 0. 3 times negative 2 is negative 6. My b is negative 5. My a is 3. So I need two numbers that multiply to be negative 6, but add to be a negative 5. So we're looking at 1 and negative 6. Negative 6 over 3 reduces to negative 2 over 1. So I can factor this into 3x plus 1 times x minus 2 and bring down my equal 0. Now I can set each of them equal to 0. 3x plus 1 equals 0. Or x minus 2 equals 0. For 3x plus 1 equals 0, subtract 1 from both sides. 3x equals negative 1. X equals negative 1/3. X minus 2 equals 0. Add 2. X equals 2. Now to check our work, I have 3 over 8 times negative 1/3 squared minus 1/4 equals 5 over 8 times the negative 1/3. 3 over 8 times negative 1/3 squared is 1/9 minus 1/4 equals 5 times negative 1 is negative 5. 8 times 3 is 24. 3 over 8 times 1/9, I can cancel my 3 and my 9. So that reduces to 1 over 24 minus, I can rewrite 1/4 as 6 over 24, and that should equal negative 5 over 24. 1 minus 6 is negative 5, so I have negative 5 over 24 equals negative 5 over 24, so my negative 1/3 is correct. Now we're ready to check 2, so I have 3/8 times 2 squared minus 1/4 equals 5/8 times 2. I bring down my 3/8 times 2 squared is 4 minus 1/4 equals 5/8 times 2 gives me 10 over 8, which reduces to 5/4. 3/8 times 1/4, I can cancel my 4 and my 8. So I have 3 over 2 minus 1/4 should equal 5 over 4. 3 over 2 can be rewritten as 6 over 4 minus 1/4 equals 5/4. So 5/4 equals 5/4. So both my answers are correct. Cubic equation in one variable. A cubic equation in one variable is an equation that can be put into the form ax to the third plus bx squared plus cx plus d equals 0. If a times b times c equals 0, then a equals 0, b equals 0, or c equals 0. In this example, solve 5x to the third equals 15x squared plus 20x. Our first step is to get it equal to 0. So I bring down my 5x to the third. Subtract 15x squared from both sides, and I get a negative 15x squared. Subtract 20x from both sides, and I get a negative 20x equals 0. Then I want to factor out my GCF, which is 5x. That gives me x squared minus 3x minus 4 equal to 0. Bring down my 5x. I need two numbers that multiply to be negative 4 and add to be negative 3. So I have x minus 4 and x plus 1 equals 0. Now I can set all three parts equal to 0. 5x equals 0, or x minus 4 equals 0, or x plus 1 equals 0. So for 5x equals 0, divide both sides by 5, x equals 0. X minus 4 equals 0, add 4 to both sides, x equals 4. X minus 1 equals 0, subtract 1 from both sides, x equals negative 1. For my check, start with x equals 0. So 5 times 0 to the third power equals 15 times 0 squared plus 20 times 0. So I have 0 equals 0 plus 0, which is correct. 0 equals 0. Next, I want to check 4. So I have 5 times 4 to the third power equals 15 times 4 squared plus 20 times 4. So I have 5 times 4 to the third power is 64 equals 15 times 4 squared, which is 16, plus 20 times 4, which is 80. 5 times 64 is 320, which equals 15 times 16 is 240, plus 80. 240 plus 80 is 320, so I have 320 equals 320. So 4 works as well. Now checking negative 1, I have 5 times negative 1 to the third power equals 15 times negative 1 squared plus 20 times negative 1. Negative 1 to the third power is negative 1, so I have 5 times negative 1 equals 15 times negative 1 squared is 1, and then 20 times negative 1 is negative 20. 5 times negative 1 is negative 5 equals 15 times 1 is 15 plus negative 20. So negative 5 equals negative 5. So all three answers are correct. Solving equations in one variable. Solving quadratic or cubic equations by factoring. If an equation can be solved by factoring, we solve it by the following steps. 1. Write the equation so one side of the equation is equal to 0. 2. Factor the non-zero side of the equation. 3. Apply the zero factor property. 4. Solve each equation that results from applying the zero factor property. Cubic equation in one variable. The solution set of a cubic equation in one variable may contain 1, 2, or 3 real numbers. Graph A shows what a cubic equation would look like with 3 real number solutions. Graph B shows what a cubic equation would look like if we had 2 real number solutions. Graph C and D shows what the cubic equation would look like if we had 1 real number solution. In this example, find the x-intercepts of f of x equals x to the third minus 5x squared minus 4x plus 20. Our first step is to replace the f of x with 0. So 0 equals x to the third minus 5x squared minus 4x plus 20. Since there is not a greatest common factor, my only choice is to factor by grouping. So I'm going to group the first two terms together. Keeping the sign with my 4x, I'm going to group the last two terms together. So 0 equals x to the third minus 5x squared has a greatest common factor of x squared, leaving me with parentheses x minus 5. bring down my plus. Negative 4x plus 20. Since my leading coefficient is negative, I need to factor out a negative as well as the 4. So when I factor out negative 4, I'm left with parentheses x minus 5. So now I have 0 equals, my greatest common factor is x minus 5 times x squared minus 4. X squared minus 4 can be factored again, so I have 0 equals x minus 5, and then x squared minus 4 can be factored into x plus 2, x minus 2, since it is the difference of two squares. Setting each of them equal to 0, x minus 5 equals 0, so x equals 5, or x plus 2 equals 0, so x equals negative 2, or x minus 2 equals 0, adding 2 to both sides, x equals 2. So we can check this by using our calculator. So go to y equals, and we want to type in x to the exponent of 3 minus 5x squared minus 4x plus 20. Graph. And we can see it crosses in 3 places. Second table, and I have negative 2, 0, 2, 0, and 5, 0. So our solution is correct. Using a quadratic function to model a situation. A quadratic model is a quadratic function or its graph that describes the relationship between two quantities in an authentic situation. For this example, we want to solve. A rectangular rug has an area of 60 square feet. If its length is 2 feet more than twice its width, find the dimensions of the rug. So we draw a rectangle. We know the rectangle is 60 square feet. If our width is x, then our length is 2 feet more than twice the width, so 2 plus 2x. We also know that the area of a rectangle is length times width. So I can set up my equation as x times 2 plus 2x equals 60. Distributing my x, I have 2x plus 2x squared equals 60. I can rewrite that as 2x squared plus 2x, subtracting 60 from both sides, minus 60 equals 0. Factor out the 2 parentheses, x squared plus x minus 30 equals 0. I can divide both sides by 2, which gives me x squared plus x minus 30 equals 0. I need two numbers that multiply to be negative 30 but add to be 1. So x plus 6 times x minus 5 equals 0. Now I can set each of them equal to 0. X plus 6 equals 0, so x equals negative 6. Or x minus 5 equals 0, so x equals 5. Since we are dealing with feet, I can't have a negative measurement. So I can rule out x equals negative 6 and will only use x equals 5. So if x equals 5 feet, then 2 plus 2 times 5 will equal 2 plus 10, which is 12 feet. So the dimensions of my rug are 5 feet by 12 feet. Using factoring to solve polynomial equations. The zero-factor property allows us to solve a quadratic equation. If AB equals 0, then A equals 0 or B equals 0. The graph of a quadratic equation will allow you to see what your values of x will equal. It will be where the graph crosses the x-axis. A cubic equation in one variable will have either 3 real solutions, 2 real solutions, or 1 real solution. Again, we can use the graph to see where it crosses the x-axis to verify our solution. Using a quadratic function to model a situation allows us to solve problems where we have to multiply, such as area.